Everyone, or actually, good afternoon. My name is Mohammed Khamis. I am presenting this on the behalf of Shahram and Diako, who unfortunately were not able to make it to the conference due to reasons out of their hands. I'll present this on their behalf, but of course, if you have any questions, don't hesitate to ask me at the end of the presentation. All right, so the thing is, one of the most common ways to interact with the web and to access new types of new information is by scrolling. So for example, on Facebook, on Twitter, whatever, you usually scroll through news feeds, and that's how you perceive or you see new content. And once you are performing these scrolling movements, whether it's with the mouse on a desktop computer or whether you're swiping on the phone, you go through three subtasks. First, you scroll, and then at some point, once you find the thing that you're interested in, you stop, and then you take some steps back in order to get the thing that you're interested in into the main view. And now, the idea behind EyeGrip, which is a system introduced by the authors, is that it automatically detects which object is interesting to you while you're scrolling, and it detects it from among several objects that you're scrolling through. The way it works is that, I don't know that you can see the taskbar. The way it works, as shown in this video, is that as you are following objects that are appearing after one another, you perform these types of eye movements. So you basically move your eyes following each object. And it gets interesting when you follow an object that is interesting to you, because this pursuit movement gets longer when you're looking at the object that you're interested in. And that's basically how this technique works. So it relies on the Optokinetic Nystagmus eye movement. And this type of eye movement is actually a combination of two types of eye movements. The first one is the smooth pursuit, which is the type of eye movement that you perform when you are following an object that is moving smoothly. So you smoothly pursue it with your eyes. And the second part of this eye movement type is the saccade, which is the common eye movements that you perform when you're reading, for example, or scanning something with your eyes. So basically, it's a jump from one point to another. So if we look again at the video that we saw earlier, first you have the smooth pursuit eye movement while following the moving objects, and then you perform this saccade in order to jump to the object that is before the following object. So for example, here, while you're looking at the green object, which is the object of interest, the smooth pursuit movement takes a bit longer. And the idea behind the system is that it detects this longer smooth pursuit movement, and based on that, it determines that this is the object you're interested in. All right. Sorry about that. You saw a graph over here, which was changing based on the eye movements. So basically, here we are. So basically, this signal is generated while you're performing this type of eye movement. We'll just abbreviate it as OKN. And what happens basically is that you see this pattern here, where there are a slowly increasing slope, which represents the smooth pursuit movement, and then a sudden drop. And this drop is the saccade. And in situations where you have a peak like that, this means that the smooth pursuit movement took a bit longer time. So based on that, the idea behind this system is that it detects these peaks, and it observes which objects were visible at that point, and it assumes that these are the objects you're interested in. But of course, these signals are not always as clear as the graph that we saw earlier. So these are examples of how this graph could look like. So it's not always obvious where these peaks are. So the authors carried out an experiment in order to test the system, EyeGrip, against several scrolling conditions, and also to build and evaluate a classifier that can detect these peaks. So in their study, they invited 20 participants, and they experimented with 3 speeds of moving objects and also 2 sizes of images. So basically, these are the speeds in visual angle per second, and they were determined based on the maximum speed at which humans can perform a smooth pursuit eye movement. Because at some point, once you show objects that are moving too fast, you're no longer performing a smooth pursuit movement, but rather a series of saccades to catch up with the object. So that's how the 3 speeds were determined. And of course, the size of the image is also influential, because the bigger the images, the less of them you can fit at one time, because the objects have to be moving in a one direction. Of course, the smaller they are, the more you can fit into the visible area at once. So they invited the participants, and they asked them to wear a head-mounted eye tracker. And on a laptop, they were watching images that are moving from right to left, images of political figures. And the task was to identify which pictures have Bill Clinton, and they should hit the space bar once they see these pictures. So that was the task that they were supposed to do. So in total, we had 6 conditions, so 3 speeds and 2 image sizes. The participants did 1 run per condition, so 6 runs each. And each run, they had 40 images, out of which 7 had the image of Bill Clinton, and the task was just to hit space whenever they see it. The gaze data was collected at that time, and before we go into the evaluation of the classifier that the authors implemented, they also looked at the miss rate or the error rate by the participants. So cases by the participants where they did not hit the space bar, although there was an image of Bill Clinton. And we can see here that in the condition where the objects were moving really fast, there were a lot of errors, and the errors got fewer as the images moved in a slower speed. So next comes the evaluation of the classifier itself. So at first, the authors excluded the 5 participants because these 5 participants were missing like more than 75% of the gaze points. So we ended up with 15 participants. Second normalization took place using the min-max method. So during the experiment, there were 2 points that appeared at both sides of the screen, and the participants were asked to stare at them for 3 seconds each. And these 2 points were used for normalization. Afterwards, the normalized data of the 15 participants was aggregated, and of course, they were labeled based on whether the participants had hit space when they saw the picture or not. So, the authors used the multi-layer perceptron algorithm in the Weka software, and they used it in its default setting, and used the horizontal coordinate of the pupil as the only feature. And for each condition, they used a window size. So basically, the window size was determined based on on pre-experimentations, where they found they picked a window size that works best for each condition. So in that case, 30 frames worked well for these conditions, 20 frames for these conditions, and so on. And next, they measured the accuracy of the classifier. So by accuracy, I mean how often did the classifier expect them to hit space when they actually hit space. And so how correctly did the classifier predict that the user is paying attention to the picture of Bill Clinton? And the repeated measures ANOVA showed that there is a significant effect of the size of the image on the accuracy of the classifier, but they found no significant effect of the speed of the, oops, is this the right slide? Yeah. They didn't find any significant effect for the speed on the accuracy. By looking at the graphs here, we can see that the bigger images resulted in higher accuracy, and that was significant. However, although it's not, we did not find any significant results here, it was obvious that the faster the images move, the lower the accuracy is. So based on these results, the authors came up with some guidelines regarding the use of EyeGrip. So although there is no limitation on the number of detectable objects, I mean the number of objects that you can show that are moving, they all have to be moving in one direction and at the same speed. So EyeGrip also works best when there is a temporal tension. So which means that we have to use a speed that is not too slow in order to ensure that there is temporal tension. So there has to be this extreme, like smooth pursuit followed by an extreme saccade, or like moving back to the previous object. But also showing objects that are moving too fast, as we've seen in the graph earlier, results in participants actually missing the objects that they're looking for. So there should be a trade-off should be reached every time a system is implemented using EyeGrip. Yeah, and one issue that was noticed during the study is that images that require a lot of attention, so for example, images that are visually demanding, will let you, I mean, participants will pay more attention to them, and as a result, the classifier might think that they are more interesting to the user. Although they're not interesting, but it's just because the participant had to look more at them in order to understand what's in them, and that might make the classifier think that it's interesting for the user, while it's not. So in addition to the experiment, the authors built and evaluated two sample applications. The first one was a simple picture selection application. So they used the winning parameters from the previous study. So they used the speed and the image size that were shown to be best from the previous study. Basically, they performed a study here where participants had to also, again, count the number of times the photo of Bill Clinton appeared. So this time it didn't hit any buttons or something. They just had to count it and just, I mean, they didn't tell the experimenter anything. And the classifier later on was, I mean, what the authors did, that they tried to see how often did the classifier really notice that the participants really saw the image of Bill Clinton. And of course, they compared this with the data that the participants gave at the end. So, like, for example, if the participants said that I saw the image 3 times, then they would know that the classifier should detect 3 cases where this object was of attention. And overall, they found that the classifier reached an accuracy of 81%, which is very close to the overall accuracy of the previous study, which was 87%, which means that the classifier still works well, even if the data, even if used with different data. The second application was what's called the so-called mind reading game. So the idea is that the participants were asked to look at to pick one of these 4 images. And they did not tell the experimenter which image they picked. And the idea was that the system would predict which image they were looking at when they are displayed after one another. And in that in this study, the system actually showed the selected image with 100% accuracy. So in each time, the system was actually able to tell which object the user is looking at. Yes, so of course there are several other potential applications for EyeGrip. So, for example, EyeGrip could be useful for scrolling through cards on Google Glass. It can be used to browse like posts on Facebook or detecting objects of interest on public display. Yeah, also one interesting application is to show scrolling text on smaller displays in order for people to read on smaller displays. And EyeGrip could be used to monitor if the user is really catching up all the words, and based on that, determine if the text should be revealed at a slower speed or so. Also, it could be used, for example, for visual inspection jobs. So, for example, on a production line, and someone is looking at the products and he detects something that doesn't look right, then the system could be used to detect that and warn the user. All right, so to summarize, EyeGrip is a calibration-free and implicit eye interaction technique that is used to select one object among other moving objects that are moving in the same direction at the same speed. It can be used in gaze contingent user interfaces to detect what draws user attention. And of course, you can also, instead of using a classifier, you can use simpler algorithms. So for example, you can just set a threshold, and whenever the peak that we've just seen in the graph, whenever the peak is above that threshold, you could assume that the user is looking at that object or paying attention to that object. So before I take questions, quickly, I would like to remind everyone that the PetMay workshop will take place in conjunction with UbiComp this year. So again, like last year, and the deadline is the 3rd of June. So if anyone's interested, we're looking forward to receive your submissions. That's all. Thank you very much.
Okay. Actually, I have a question.
Yeah.
So the tasks that you evaluated were like search tasks where you have a known target in mind.
Mm-hmm.
Can you speak to how it might change when you're in like a browsing task where you're not sure sort of what you're looking for and you might be interested in several things that are scrolling past?
Well, the thing is, so if you're browsing like different like through content that you're not aware of beforehand, basically we'll just notice. We'll look for that peak signal, and at that point we'll see which object is in view, and that is determined that the thing you're looking at. I don't know if this answers the question.
Sure.
Yeah. All right. Great. Okay. Thank you very much.